Okay, so welcome back everyone. So I guess this should be the last lecture. So I feel like I have to try and say something about the integral system that's really involved, because so far we really have only a phase space to deal with, right? So, So let me consider for the time being, let me try to just consider Higgs bundles and not this twist of them. So then we defined a moduli space of Higgs bundles on a Riemann surface C. My notation for this was, so you have to fix rank and degree. And degree D. Okay, so I guess the first question is, to what extent, if we're going to talk about an integral system, we need a symplectic form. But we saw that this has the cotangent bundle to the moduli space of stable vector bundles of the same rank and degree as an open subset. And this carries. So, on which we have the standard symplectic form. So it's at least clear that away from some subspace, which is actually of codimension 2, you have a symplectic form here. And exactly this codimension 2 property means you can try to extend it over there. And I guess geometrically, this symplectic form comes from Serre duality. So the deformations to the moduli space of vector bundles. So a tangent vector is given by an element of H1 of the endomorphism bundle. And so this is dual. Two sections of global sections of this twist of the endomorphism bundle by the canonical bundle, which is exactly where our Higgs bundle lived. So at least if you're at a stable bundle here, this gives you a tangent vector, and this is a cotangent vector. Okay. So that's to sleep something slightly under the rug, which is if you really think of the part of this that comes as a cotangent bundle, then it's not entirely obvious that the tangent space to this cotangent space really splits like this. I mean, in reality, there's a short exact sequence, and you need some notion of splitting. but it's kind of okay because this has a, being a cotangent bundle, you don't just have a symplectic form, you have a sort of Liouville one form whose exterior derivative is that, and that is what provides this splitting. So in any case, we have this symplectic form with which to work. And then we defined the Hitchin fibration. I can't remember whether I gave this a name. Pi is totally overused. Let's call it H. From this moduli space. To this vector space, which does nothing but take our Higgs bundle and map it to the components of its characteristic polynomial. Okay. And the key fact is that this is this is a Lagrangian fibration. That's to say, the symplectic form vanishes identically there. So I guess in the language of integral systems, this amounts to saying that if I look at the Hamiltonian the Hamiltonian vector field associated to any function on this moduli space, which is coming from a function down here on this space. So I pick any element. And this is a vector space, so it's very easy to construct functions here. So if I take a function which factors through the base, look at its Hamiltonian vector field, if I pick a maximal number of linearly independent such functions on this linear space, then their Hamiltonian vector fields commute. So it's easy to get a maximal given this fact, which is a bit non-trivial. I'll try and give an explanation for it a bit later. You get Hamiltonian vector fields. Coming from linearly independent elements of the dual vector space. Okay, and we've already seen that, we've already seen that the dimensions of these spaces really match. So, about there for a second. So the Hitchin fibration gives this space, moduli space of Higgs bundles, makes this into what is generally known as an algebraically complete integrable system. So that is to say, by these, choosing a basis of elements here provides a maximal set of commuting Hamiltonians, and the fibers of this map, as we've seen, so the Higgs fields with a fixed characteristic polynomial form a Jacobian, are parameterized by the Jacobian of a spectral curve. So the tori, which you get as fibers of this map, are really algebraic tori given by Jacobians of the spectral curve. Okay, so this is the titular integrable system which we're trying to talk about. So perhaps I can say a couple of words of what happens when d is not 0. So well, I guess it's clear that the space is not necessarily symmetric, not necessarily symplectic, because even for dimensional reasons, you can not necessarily of even dimension. But it is a Poisson variety. So there is a Poisson bivector, only that it degenerates, and the sort of I think the way to see this, which is in a very in the spirit of these lectures, which is to stick in the algebraic realm, is to view it as a subspace of another symplectic variety. Namely, you can consider the moduli space of vector bundles on C with a I never know whether to put D before or after level. People do different things. A D level structure. So I can call this so that is a pair of a vector bundle is E and eta. So E is a vector bundle, and eta is a trivialization over D. That's to say, I give an isomorphism from the restriction to D to O of D plus N. So this is this sort of artificially puts in some extra data, which is to give a fixed isomorphism of the fiber. I mean, if you imagine D being reduced for the time being, then this is just a vector space, and this is just giving you some fixed isomorphism of this to this vector space. Sorry, this is a bad place to put it. Right, so if the same thing. So if this divisor is reduced, then this amounts really just to giving an isomorphism between the fiber over the points of the divisor with a fixed vector space. So it introduces a sort of a G, an extra GLN, right? So it's a GLN bundle over the original guy. And then the tangent space to this guy is H1 twisted by O minus D, so that which is saddle to the to the space of D-twisted Higgs fields. Yeah, I apologize if I use K and omega interchangeably. I hope that's yes. Okay, so this allows you to think of some bigger space, whose tangent space, at least at a stable point here, a smooth point here, is exactly scheduled to the space of D-twisted Higgs fields. Okay, so there's this larger symplectic space. D. So this is a awesome or an open subset, large open subset. Is a Poisson subvariety of the cotangent space to this moduli space of vector bundles with level structure. So one way of getting back into the symplectic realm is to make your space bigger, but this comes at the cost of losing the integrable system structure, because these extra directions do not carry this Hitchin map, which gives you this the integrable system we want to study. But on the other hand, symplectic leaves, so maximal symplectic leaves, of this Poisson variety are given by fixing the co-adjoint orbit of the principal part of the Higgs field. So there's sort of two things you can do. You can make this space, because your problem on the face of it, if you're considering this moduli space of de-twisted Higgs bundles, is that you have this as your space of Higgs fields, but you have this as the cotangent space, the tangent space to the space of bundles, this untwisted guy. So you can expand this moduli space of bundles, you get this bigger symplectic space, that's fine. But you don't have the integral system structure there. On the other hand, you can make some choices on how your Higgs field has to behave exactly at this polar divisor. So you can fix its co-adjoint orbit, and then if you do that, you have a maximal symplectic leaf, and then the Hitchin fibration gives these the structure of an algebraically complete integral system. Right, so I guess yes, go ahead.
What do you mean by the principal part of it?
So, yeah, perhaps it's good to do an example and then we can see what we mean. So, well, what do I mean? I mean, it's easy if D is reduced, right? Unfortunately, I guess and that's perhaps an example that I will do now. So if your divisor is reduced, it's just the sum of points, then what I'm trying to fix here is exactly the how do you say, so I can then look above every point of that divisor. This Higgs field then has a simple pole there at most, right? And I can fix the GLR orbit of that principal part. So should I try and make that explicit? So, yeah, so I mean, there it's essentially a residue, right? I mean, if you like. And I tried to formulate this slightly more generally to allow for a general divisor, but I'm kind of, but that's a good, maybe it's worth making explicit. So suppose that D is reduced. points. It's an effective divisor, so just positive coefficients. Then at each pi, we have a Higgs field, which is going to look like some matrix times dz divided by z in a local coordinate. Pi. And then the maximal symplectic leaves are given by fixing the GLR orbit of so let's call this A of A. Right, so I don't know. So I guess I will do an example now where the rank is 2 and I impose this SL condition. So this is going to amount to like choosing one eigenvalue.
What's R? The number R?
Sorry, R is probably N, yeah. So I mentioned it was matrix. I can't seem to decide whether I want to write R. Yeah, I apologize. Okay, so yeah, let's see if we can be concrete in the example. So I think this is perhaps a slightly different example to last time, but very much similar. So it's entirely in the same realm. So let me consider so I'm going to look at Higgs bundles, twisted Higgs bundles on the projective line again. But instead of last time looking at some non-reduced divisor here, so last time I chose this divisor to be 4 times a point, I'm going to look at the sum of 4 distinct points. So then we can think a bit about and I'm going to impose the condition of having trivial determinants. And of rank 2. Okay, so that means one can think about the analogous space, which I think I was calling this. So SL2 Higgs bundles twisted by this divisor. And we decided that this had, well, so as we saw right now, right? So it's not quite the dimension of the cotangent bundle to the moduli space of bundles with a fixed of rank 2 with a fixed determinant, which is that. I have to add on the degree of the divisor. So this is 4, right? Because I have 4 marked points, but I have to add on another 4 for the degree of the divisor. So this amounts to being 2 plus 4, which is 6. So the big moduli space, this has dimension 6, but what I'm interested in is the maximal symplectic leaves, and they have dimension 2, and the way you get them is exactly by fixing the orbit of this principal part. So a Higgs field is given by, so I'm allowed a pole at each of these 4 points. So and then I have some matrix. To get down to a symplectic leaf, I want to be fixing the conjugacy class of this matrix, and it being of trace 0, because we impose this trivial determinant condition. If you suppose it's furthermore diagonalizable, then that amounts to really fixing an eigenvalue. So a possible Higgs field here might look like something like this. Yeah. And in fact, this the symplectic leaves are really products of coadjoint orbits. Oh, well. So in this particular example on P1 with 4 points, there is not enough space for anything more interesting to happen. So a Higgs field in the maximal symplectic leaf really is determined exactly by really is just given by the elements of the coadjoint orbit that you're fixing at each of the 4 points. There's nothing more to it. So this is
these matrices are diagonalizable.
Well, you don't have to make that choice, but it is a possible choice. So there, so basically here you're interested in how SL2C acts on the space of all 2x2 matrices, and well, so if you we can think just about trace 0 matrices. So if you are diagonalizable, then you're conjugated to something of this form, and if you're not, then So if, I don't know, what do we call A? So if A is diagonalizable, then A is conjugate to something like this. And if not, it's going to be, well, you have to have 0, 0, 1. Right?
My question was that, like, these four metrics are simultaneously diagonalizable and they commute.
Well, so what you can ask to get a symplectic leaf here, which is where the phase space of the integral system you want to study, is you can demand that your Higgs field belongs, so the how do you say, this polar part of the Higgs field at each of the 4 points belongs to some fixed orbit here. You're free to specify that. That's not to say that you can simultaneously diagonalize all of those matrices, only that it belongs to that orbit. So you're essentially just fixing an eigenvalue. If they all are on their own diagonalizable, you're fixing their eigenvalue, but nothing more.
But as far as I understand, nothing changes dramatically in your construction if these are not diagonal.
No, I mean that's a perfectly good choice. It just means that something slightly different is going on. I mean, so at that point, it might be interesting to look at what's happening at the level of the spectral curve. So I mean the spectral curve is given by, well, there's only one sort of interesting element here, right?
No, I was asking this just because so far I see, so the Hitchin systems I have seen are connected to gauge theories or string theory.
Right.
And the Higgs field is usually here. This field is in diagonal form in but apparently your construction is more general.
Yeah, it doesn't have to be. So I mean, what is going on if you so where did this live? So this has to reside in the total space of the twisted cotangent bundle. So what's going on is if this the Higgs field is diagonal, or the principal part of the Higgs field is diagonal at one of these points, then that means you're not at a branch point of this spectral color. So this maps back down to P1. And this being diagonalizable is the same thing to say that this cover is what do you say? Unbranched, not branched at Pi, because I mean, what are you getting? You're getting exactly the eigenlines of this matrix as your cover. So this is so choosing this sort of nilpotent form for your Higgs field is to say that a branch point of this the point, how do you say? If at a point the leading the principal part of your Higgs field is nilpotent, then this cover is really branched over that point. Another way of saying that might be, this is also to say that this really has a pole of order well, I have to be a bit careful there, of order 2 in this case, but pi. So if you think about the determinant, this lives in here, so it could so it's a quadratic differential, but well, perhaps the neater way of writing it is like this, but this is the same thing as so you have the determinant of this, like the target of the Hitchin map is a space of quadratic differentials which can have poles of order 2 at your points of your divisor, and to say this is to really say that you actually do have a pole of order 2. There's nothing to say that a section of this can't have a lower order of pole, and choosing this nilpotent form really does give you such. So, but yeah, you have a good freedom of choice, let's say that. So. Yeah, so I guess this example is one of many. So, so within so for D on P1 with degree of D being 4. Our choices for the type of the divisor. So if I just write the multiplicities of the points, then perhaps it will be clear. So, so generically, you have 4 points with multiplicity 1. So that's the multiplicities. That's the situation I've just been talking about. And then you can start to make these coalesce. So one can have 2 plus 1 plus 1, and then one has a few choices. One can have 2 plus 2, and one can have 3 plus 1. And then both of these can coalesce to give you a single point of multiplicity 4. These sort of give you sort of integrable systems of the lowest possible dimension by studying symplectic leaves of the moduli space of D-twisted Higgs bundles with D of these types. So this one, I guess, we saw an example of this last time. Studied, here it really amounts to polynomial matrices, and we studied that. This is this example. This is the sort of more generic type of divisor, and these coalesce into each other. And there's a whole parallel story to these, which I guess I won't talk about, but I think it's good to mention. So every Hitchin system there is an intimately related Isomonodromic deformation problem. These give you the simplest isomonodromic deformation problems, namely those whose solutions are given to you by solving Pan-Lavie equations. So this is, in some sense, if you want to get to grips with Higgs bundles, then I think this is the good playground to try to play. Okay.
Confused, can I ask
Yeah,
something?
go for it.
So you said in this case the symplectic leaves have dimension 2.
Yeah.
So the spectral curve should be an elliptic curve, I guess.
Yeah, the spectral curve really is an elliptic curve. Yeah.
But if you're in the total space of KP1 twisted by degree 4 divisor, that's O2, right?
Yeah, so here you're in.
So you always have a branch to 2 points, which would give a P1.
Well, let's see. Hopefully this works out. So, yeah. So what's going on? I don't see. Let me write you an equation and try and convince you that we have an elliptic curve here. So what was I said what the Higgs fields should look like. So I mean, one perfectly good Higgs field with a given choice for these orbits is would be this. And then what is the equation of the spectral curve? It's exactly, this is the determinant of this Higgs field. So you have to go and think about what this determinant is going to give you. So, well, what's going to happen? You're going to, so this is the same as I sum inside, right? So I've got the sum of so I guess the so the determinant of this is then this 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 product. That's the determinant of the leading part, right? This squared. Right, so does this look like an elliptic curve? What would I do? So if I'm to expand this, then I would have to try to put everything over a common denominator. I guess each term can have only one of the z minus pi's.
There would be an easier way to reason just by the degree of the.
Yeah, we should. Yeah, the degree should work out. So if I've written the wrong degree, then it's. But yeah, so what's happening?
No, but we can talk about it later. It's more useful.
Yes, okay, we should try and get it right. So, yeah, so how would you right. I mean, So, yeah, what do you get here? You can put this over a common denominator where you just have this in the denominator, and then you have products of pairs in the numerator, right? So it's going to look like that. I think that is the equation of an elliptic curve. Yeah, I guess another way to think would be what are the branch points of this, right? So I mean, as we said, if this thing lives here, then the determinant of it really belongs to this, right? 2D. So this is over 4, yeah. So right, this is over 4. This guy should have 4 zeros somewhere, which are exactly the range points. Yeah. Okay, what was I going to say? Okay, so yeah, perhaps I can say something more general again. So, Hitchin systems have a lax representation. So I guess we've seen we know that the conjugacy class of a Higgs field in a given fiber of the Hitchin fibration is constant. So, I mean, the Hitchin map is giving us exactly the spectral data, if you like, of the Higgs bundle. So, the Hamiltonian flows must preserve the spectrum. And this is all meant in a sort of global sense over the Riemann surface C. So there's a spectrum at every point of the base curve C, and this is preserved. So the sort of natural setting for that is that the differential equation that these Hamiltonian flows give is given by the lax formalism. So if we have so consider imagine I have an L, a matrix L, which depends on T. Then if I make it vary by fixed n, so if I consider a variation of it such that the derivative is given by commutating with some fixed matrix, then the spectrum of this does not change. So, invariant. So, in the context of Higgs bundles, we have this globally over the curve C. So if we pick a local coordinate on C, then you have this same situation, except that you now allow your matrices to depend on this coordinate on your curve. So I guess in the integrable system literature, I mean, this sort of concept of a lax pair involving a spectral parameter, I think even predates this knowledge of this study of Higgs bundles. But it's really to note that you can take any Riemann surface here. So I think in the integral system literature, one often considered, you often have C as P1, at least secretly, I guess. A lot of the integral systems literature does not make it explicit the geometry, but I just view this Z as some parameter, but the sort of the global behavior at infinity can be formulated in the framework of Hitchin Integrable Systems on the projected line.
So this is a stupid question.
Yeah.
You're just saying L and M are Higgs fields and L depends on T. So I didn't, yeah, okay. So perhaps this is unfair the way it's written, yeah. So what I'm trying to say is we have Hamiltonians for the Hitchin integrable system. Okay, so if I have a Hamiltonian vector field, then I can write down, what do we know about it? Well, it preserves the fibers of the Hitchin fibration. So it's a flow which preserves the spectrum of this, of the Higgs field L at every point. Yeah. Okay, and I'm saying that a framework for achieving that is this. That the flow is actually given by the commutator with something else. So if I have this situation, then I know that the spectrum of this is invariant. So I'm saying that a lot of the lax formalisms that exist in the classical integral systems literature actually can be formulated in terms of these being exactly Hamiltonian flows for Hitchin systems. And
in fact, moreover, you can really have a lax formalism for the Hitchin system. So it's the way I've introduced the Hitchin system. It's perhaps not so easy to see because I've hidden the original origin, which is this gauge theoretic origin, where this is really clear where this lax pair is coming from. But it's really true. So Hitchin systems have this lax formalism available to you with a parameter, and the parameter has to be understood as a coordinate on the base curve C. Right. So, and moreover, we have a separation of variables for Hitchin Integrable Systems.
So for Iogene's Riemann surface, you put in M a section of endomorphism of E?
You're asking what is this object globally? Yeah, that's a good question. That's something I would have to think about. So let's see, where is it really coming from? I mean, it's coming, I guess it comes from the fact that you can consider, you have not just eigenvalues, but eigenvectors. So one can, let's say this. So I guess if you can think of an associated two associated linear problems here. If you have this lax formalism, namely you can ask for finding eigenvectors of L, and then you can construct M via the variation of these eigenvectors. So yeah, what that quite is for a global object escapes me right now, but this is, maybe we can talk about it afterwards. Okay, so yeah, I wanted to say here that separation of variables also exists. So,
sorry,
yes.
This is a silly observation. In any case, there is a whole theory to construct. Not every M is compatible, no? So we have some classifications of
yeah, you
and different sort of this kind of classification of compatible flows. So not for any M that differential equation should make sense, no? So you have a construction given an M of an entire class of of M.
So yes, it's
not always you get probably an Hitchin system inside. You get other stuff also.
Yeah, for sure. So this lax formalism is very general. I'm just trying to say that the Hitchin systems do fit inside it if you're willing to understand the parameter as something that lives on a Riemann surface. And yes, the M is so to achieve the Hamiltonian flows you want, you of course have to choose it wisely, but it's also not a unique object, unfortunately.
No.
So it's again, it's a sort of a cohomology thing, really. So if you interpret these objects globally correctly, then this M belongs to an appropriate cohomology, an appropriate cohomology group. And I think it's easiest to see it up on the spectral curve, where you have the spectral curve being defined by the eigenvectors and been defined as the locus of the eigenvalues and with its line bundle given by the eigenlines. So via this BNR correspondence. And then
you should have also a similar equation for M.
Say again? Yes, right, exactly.
That exists with the compatibility.
Yeah, the compatibility you have to write it.
A second linear problem.
Yeah, a second linear problem, which is to do with the variation of the eigenvalues. I'm sure someone who's an actual integral systems expert will happily correct me. I'm going to write this wrong, I'm sure. So something like this, maybe. Right, we can think about whether that leads to compatibility. But yes, I mean, so sort of downstairs, I think this is slightly unclear, but in this interpretation of the Hitchin system by the BNR correspondence, so as pairs of a spectral curve and a line bundle, then this is, so this is to do with how a section of the line bundle, this eigenline bundle, is varying. So to this problem. So constructing this is really constructed out of a cohomology class of the line bundle. That's really the freedom you have to choose. Right. So I wanted to say this furthermore. So I mean, one plus of the Lax formalism is it gives you a way to try to separate variables. So here, so I guess if we consider Higgs bundles, with the underlying bundle, the trivial vector bundle. These arise by pushing forward line bundles of degree G, or G being the genus of the spectral curve on the spectral curve. So I guess we spent some time thinking about the case where the degree was G minus 1. But we said this last time as well, that the push forward at least of a generic line bundle of this degree on the spectral curve gives an underlying trivial bundle. So pushing forward a generic, let's say. So if you consider a generic line bundle of that degree, then it has a unique section up to scale. So a generic line bundle. Up to scale, which vanishes and visits of degree G at precisely G points. So we get coordinates. Let's say Zi, Yi, in the where the spectral curve is defined in the total space of this. Well, it's not twisted by D. The total space of this line bundle. For which are Darboux coordinates. For the symplectic form. So, I mean, to parameterize the moduli space of Higgs bundles, what do I need? Well, the dimension of the base and the fiber of the Hitchin bundle is G, the genus of the spectral curve. So if I give you two numbers from I equals 1 to G, I have the right number. I have the correct number of coordinates. And they really give canonical coordinates for the symplectic form involved. So I guess more formally, there is a symplectomorphism, a birational. So it's not quite the correspondence you'd like, but it's birational. From the moduli space of Higgs bundles to, well, I guess the Hilbert scheme of G points on the cotangent bundle. So that's to say, essentially, just the symmetric product of points on the cotangent bundle, and it deals with the situation where they flow together. So in a sense, Hitchin systems can really be solved in a strong way. So this is in a sense, at least you can reduce it to a bunch of one-dimensional problems. No, this is really G. So G in so G, obviously these things should depend on each other somehow. Okay, so it really doesn't depend on the degree. I mean, to give the morphism requires giving the degree. It does depend on the rank. So I'm not sure if we ever wrote a formula for the genus of the spectral curve in terms of the data downstairs. Yeah. But it's a Riemann-Hurwitz computation, right? So G is related to the genus of C, so G being the genus of sigma, is related to the genus of C and the rank M by a Riemann-Hurwitz computation. So So that's to say, you're trying to compute the degree of an n-to-1, trying to compute the genus of an n-to-1 cover of the surface of the Riemann surface C, and you can write down a pretty neat formula for computing the genus of such covers, essentially from the Riemann-Roch theorem, if you wish. I'm not going to try and do it from memory. I don't know. Do I dare? I mean, it's the same as the dimension, half the dimension of this. So, which I guess we did write down in the general case, right? We worked out what it was. It was that really was this Riemann-Roch computation. So I guess G has to be let's see, n. So yeah, n squared times the genus genus of C. Yeah, n squared times the genus of C. Minus 1 plus 1, I think. Okay. So in particular, this is a surface, so it's two-dimensional. So this is 2 times g-dimensional. So this should be the dimension of the dimension. Half, so yeah, this G should be half the dimension of this, which is to say the dimension of the moduli space of vector lambdas. Okay, and this again has antecedents in the integral systems literature. So what you're doing here by essentially picking out the eigenvalue of the Higgs field at these vanishing points. So picking out these vanishing points in the corresponding eigenvalue of the Higgs field is known prior. So getting at these G points is the same to get at poles of Baker-Akhiezer functions in the integral system, in the old integral systems literature. Okay, so yeah, so you have this separation of variables, and maybe I can I sort of did it for you in the example I had up last time, so maybe I can perhaps I can finish even by recalling that example. So we had the example where we were looking at P1, the divisor D being 4 times infinity, and the leading term of the Higgs field at infinity being nilpotent. And I really tried to work through what was an effective parameterization. So if this is going to be nilpotent, then I mean the leading term of the Higgs field is has to be Z squared, right? So what you get is Z squared plus something. Everywhere else has to have a 0, and the freedom of conjugation of acting by Möbius maps on P1 allows you to eliminate a few more terms. So you can make this constant, and you can make you can insist that if you like, the center of mass of the zeros of the quadratic differential you get as its determinant is 0. So you can reduce everything to this form. And for some reason I like to write the constant term like this. So I mean, this term you can't fix, but I write it as q squared plus a, so that the determinant is minus p squared, and then this is arranged so that this goes away. Here I get this a, which is why I wrote it like that. And then I get the same thing with q. Okay, so here you have this Hitchin integrable system where really the spectral curve you recognize as an elliptic curve in Weierstrass form, if I were to write it with this this rather funny constant term. Right. So this is already the sort of naive reasoning I was trying to give less time to develop. This really is actually implementing the separation of variables in this case. So an open set of the moduli space. And this, is parameterized by P and Q. So where and the symplectic form is dp wedge dq. So the open set that's being parameterized here is exactly those Higgs bundles for which the underlying bundle is trivial. So I can think of varying P and Q. And what you might recognize is not only the Weierstrass form of the spectral curve here, but if you look at the constant term of it, you see again a Weierstrass form of an elliptic curve. And that's not an accident, of course, because the fibers of the Hitchin integrable system are indeed elliptic curves. And because the Jacobian of an elliptic curve is isomorphic to said elliptic curve. So really these P and Q give these natural coordinates, and the Jacobian is cut out by exactly this equation. So this constant term here, as we expect, is the Hamiltonian for the Hitchin integral system, and being on a fixed value of the Hamiltonian is to be on this particular Jacobian. Right. So it sounds like this is, I guess, feels like a lot of complicated machinery, but in reality, in the simple examples, it works out to something pretty concrete. Right, how much time do I have? Not much. Okay, so let me say one more word. So I guess one can imagine what happens if you try to move. If you try to move off this big open set, so what happens if you somehow are unlucky and end up with a Higgs bundle which is not on the trivial bundle? And I guess we saw precisely when that should happen. It should happen exactly when the corresponding line bundle on the Jacobian of the spectral curve is a twist of a trivial line bundle. So, and yeah, you really see this happening here. So there's, in fact, we see that there's sort of 1 point missing in every fiber, because this can only parameterize the affine part of an elliptic curve. And what's missing from the Jacobian is the point at infinity everywhere, right? And the point at infinity is exactly when this Q goes off to infinity, and then this parameterization starts to make no sense. But that's to do with the fact that the bundle is jumping from the trivial bundle to a direct sum of non-trivial bundles. And then this going off to infinity, you can kind of try to divide by it, and that includes it up here. And then you get exactly this Hitchin section. There's exactly a section which is missing. This is a thing I wrote on the exercise sheet from last time, and that's what's missing from here. So we miss. So this birational morphism missed out exactly the Hitchin section. Namely, bundles over 1 plus over minus 1, and this being everything. This is just a Hamiltonian at this point, so I don't know. Makes it look like I've parameterized it too much, right? It should be parameterized by one number. Okay, so I think I should. Oh, you have a question? Go on, last question before I officially close. Right.
Recognize.
Yeah, you can recognize the first Pan-Levé equation.
Yeah, something like. And then this point Q corresponds to a call.
Right. So I don't know. This is. I attempted to make a remark in the middle to say that indeed to every Hitchin integral system there's a closely related Isomonodromic deformation problem. Yeah. So I can perhaps try to do this in the example and try and say what the general formalism means. Quick. So what's going on? So I guess we have a Higgs field, right, which is a twisted endomorphism. And let's suppose E is trivial. Then, so this is really what algebraic geometers like to say is O-linear, which is to mean if you apply it to a function times a section, you get it applied to, you get the function times it applied to the section. So that's not what a connection looks like, but this is a connection. So then this is indeed a flat connection on the trivial line. And then you can wonder, so if you have flat connections, you can ask, how can you deform flat connections in such a way that their monodromy remains the same? So this is the topic of isomonodromic deformations. That's a good question, and a sort of a cheap answer to it is that this data really depends upon the choice of a complex structure on the curve, on the Riemann surface. Whereas the monodromy of a connection has, does not see the complex structure. It's an entirely topological construct. So what one expects is that there's really if you like, a connection in the space of this data over the moduli space of complex structures on the Riemann surface, along whose flat sections the monodromy does not vary. So that's what you should have in mind. Unfortunately, here it's all a bit obscure because I'm on P1, right? So what should be the modulus of the complex structure of the base curve? Well, P1 you think doesn't have any. In fact, perhaps has negatively many. But what it should actually be is in the in exactly the data that you're fixing at the Higgs bundle at a pole. So the way to turn this into a sort of isomonodromic deformation problem is to think of this as a time. Right, and then one can write down a very similar. Well, you can write down exactly a similar lax formalism. You have to deal with the fact that you have a T. Only that you've now really introduced a time dependence into your Hamiltonian. Yeah. So if you like this Higgs bundle system, if you think about how P and Q have to vary, if you flow along the sort of standard, along this Hamiltonian, then it's exactly given by, that pen isn't very good. It's exactly given by P varies, the standard formalism. P varies according to the derivative of H with respect to Q, which is something like Q squared plus something. E probably, and Q varies with respect to P. And here you recover exactly the same thing, only that you had this explicit time dependence in your Hamiltonian. So if one is really careful, one can try to study what happens as you try to take this situation back into here. And the way to do that is to think of not connections but lambda connections. So you have this extra parameter here, and you know another color for it. So that when you take lambda towards 0, you recover this. And if you do that carefully enough, you can recover the Hitchin Integrable System from this isomonodromic, from the Pandelay equation in this lambda goes to 0 limit. So what happens is the sort of isomonodromic flow, it sort of starts to wrap more and more around what look like fibers of the Hitchin Integrable System. There's a sort of like a sort of set of fast times that you can isolate which wrap around these fibers. Anyway, that was far too long an answer for a question.
Okay,